8-2 special right triangles. The first special right triangle we deal with is the 45, 45, 90 triangle. And this theorem tells us that we have both legs congruent in this triangle. Since we know we have two 45-degree angles, the two legs would be congruent to each other. That's from the converse of the isosceles triangle theorem. So we could say both of those are x. And the hypotenuse then would be square root of 2 times the length of one of those legs. So we label that as x square root of 2. So this triangle is something that you're going to want to study and be able to reproduce so that you have what are called the generic side lengths of the 45, 45, 90 triangle. Now, where does this come from? How do we develop this theorem, or how can we show that it's actually true? What we can do is we can take a generic square that has side length x. And now to create a 45, 45, 90 triangle, we can draw in a diagonal. Now we know that a square is a rhombus, and within a rhombus, one of the properties is that the diagonal bisects the two angles. So that means if it's bisecting a right angle, which is 90, you'd have 45-degree angles. So now that we have right triangles, we can solve for that hypotenuse using the Pythagorean theorem. So we would be able to take x squared plus x squared and have that equal to c squared. Now combining like terms, a little algebra, you have 2x squared equals c squared. And then to solve for c, you take the square root of both sides. Now thinking back to simplifying radicals, we can apply the same type of concept when we just use numbers to also being able to simplify with variables. So the x squared is a perfect square factor, so I can take the square root of that, which means it moves outside. And now we have that length of the hypotenuse being x times the square root of 2. No matter what the value of x is, no matter what the side or the length of those legs are, this x times the square root of 2 will be the length of your hypotenuse. So a few examples using this theorem. Here we have a 45, 45, 90 triangle. We know the legs are 9, so even though one is labeled, we would have to know the other one is still 9. Now to find the hypotenuse, we have to look back up at our 45, 45, 90 triangle theorem. The hypotenuse is always the leg multiplied by the square root of 2. So that means if you take 9 and multiply by the square root of 2, you can't simplify those numbers at all. So that h is just 9 square root of 2. In B, we would have to recognize this as a 45, 45, 90 triangle, because if it's an isosceles right triangle, the two angles that are remaining still have to be 45 degrees. Now again, we know the legs, and we're trying to find the hypotenuse. So we have to take the leg and multiply it by the square root of 2. So again, going back to our simplifying radicals, we are able to multiply outside numbers with outside numbers, inside numbers with inside numbers. So we would get x equals 4. And then part C, little different between A and B, because now you know the hypotenuse and you're trying to go back and find a leg. Well, if the hypotenuse is represented by x times the square root of 2 and the leg is represented by x, to go back to just x, you'd have to divide by the square root of 2. So we have 6, which is the hypotenuse, divided by the square root of 2. Now, we're going to simplify this by rationalizing that denominator. So we have to multiply by the square root of 2 over the square root of 2, which gives us 6 square root of 2 over 2. But now, 6 and 2, both outside numbers, we would have to reduce those whenever possible. So in this case, the value of y is 3 square root of 2. The last one in this section, still using 45, 45, 90 triangles, I'd like you to find the length of a leg given that the hypotenuse has length 10. Here again, we're going from the hypotenuse back to a leg, which means we have to divide by the square root of 2, which means you have to, again, rationalize that denominator, and then simplify to get 5 square root of 2 for the length of your leg. The second type of special right triangle is a 30, 60, 90 triangle. Within a 30, 60, 90 triangle, there's three different side lengths because none of the angles are congruent to each other. So what we do here is we give these specific names. So we have these three labels that we can use for a 30, 60, 90 triangle. SL stands for shorter leg, LL stands for longer leg, and H stands for hypotenuse. Hypotenuse should be the easiest one. It's still always opposite from the right angle. We know the shorter leg has to be opposite from the 30-degree angle because it's smaller than the 60-degree angle. We had inequalities in triangles earlier this year that told us the shorter side is opposite the smaller angle. And then the longer leg is opposite the 60 every time. So within this triangle, what this theorem tells us is that the hypotenuse is always twice the length of the shorter leg. So if the short leg is x, the hypotenuse will be represented by 2x. So the hypotenuse, again, 2 times that shorter leg. The length of the longer leg is square root of 3 times the length of the short leg. So longer leg would be x times the square root of 3. So again, this generic side length triangle is something that you're going to want to study and make sure that you can remember so that you can use these properties to help you in the problems that you'll have to be able to complete. So now again, where does this one come from? Where does this theorem come from? So a lot of people want to say that a 30, 60, 90 triangle always comes from a rectangle, since the 45, 45, 90 came from a square. It actually always comes from an equilateral triangle. So we know that an equilateral triangle is always equiangular as well, so I've marked the angles to be congruent. Now, if I know this is equilateral, I know all the sides are congruent. So I'm going to label those two sides as 2x. What I also want to do, in order to get that 30, 60, 90 triangle, I need to draw in an altitude. So now we have to remember, because an equilateral triangle is also an isosceles triangle, when you have an altitude of an isosceles triangle, it is the angle bisector of the vertex. So here I have the angles being bisected up top. And it is the perpendicular bisector of the base. Now, if we know all the sides of the original equilateral triangle are 2x, and this altitude is a perpendicular bisector of the base, this is how we could easily show, just using some of the properties from the past, that each of those shorter legs would be just x. Now again, going back to the actual angle measures, if it's an equilateral triangle, it's also equiangular, which means all three angles have to be the same, meaning they're all 60 degrees. So when I bisected that vertex angle, that's what gave me my two 30-degree angles. Now that I know that I have x and 2x for side lengths, I could figure out the length of that altitude by using Pythagorean theorem. So a squared plus x squared equals 2x squared. Notice how the 2x is put in parentheses because we're squaring that entire term. So that's one mistake a lot of people make, is they forget to square the coefficient of 2. You have to think 2x squared means that you're taking 2x and multiplying it by 2x. So the 2 times 2 would give you 4. The x times x would give you the x squared. Or you can think about it using exponent properties. You square the 2 coefficient and you square the x variable. So now we're going to subtract x from both sides. So we have a squared equals 3x squared. Take the square root to figure out what a is, and then simplify, and we would find that a is always going to be x times the square root of 3. And that a in this case represents the longer leg of that 30, 60, 90 triangle. So a couple examples of 30, 60, 90 triangles now. One extra note for you to add. You must find your shorter leg first. If you're not given the shorter leg, you must find the shorter leg first, because that is the side of the triangle that the other two are related to. So if you have to go back to the short leg first, then great. If you already know it, then you can figure out the hypotenuse and the longer leg in whichever order you'd like. So in part A, we have to find the value of D and the value of F. What I recommend students do is label the sides of the triangle. So if I know the 5 is opposite from the 60-degree angle, that's going to be the longer leg. F is the hypotenuse because it's opposite from the right angle. And D, the D variable, would be the shorter leg. So now I have to find the value of D first because I don't know what the short leg is. If I don't know it, that's the first one I have to find. So that means I have to take the longer leg, since that's the piece that I'm given, and to go back to the shorter leg, I have to divide by the square root of 3. Now, dividing by a square root means we have to rationalize and then simplify. We would end up finding that the value of D is 5 square root of 3 over 3. Once we have that shorter leg, we can find the hypotenuse in this case. Hypotenuse is twice the shorter leg. So if I take 2 and I multiply it by this 5 square root of 3 over 3, we have to remember that 2, written as a fraction, has a denominator of 1. So I can multiply the numerators. 2 times 5 square root of 3 gives me 10 square root of 3. And then the denominators, 1 times 3 is 3. I can't reduce the 10 over 3, so 10 square root of 3 over 3 is just the value of F. Go ahead and try part B on your own. In part B, we're given the hypotenuse. The X variable represents the short leg and the Y variable represents the long leg. So again, not given the short leg, it's got to be the first one that we find. Going from hypotenuse to short leg, you divide by 2. The hypotenuse divided by 2 is the shorter leg, so in this case, X equals 4. And now once we have X equals 4, to go from the short leg to the long leg, we just multiply by the square root of 3. So 4 square root of 3 is the value of Y. Also like you to go ahead and try number 5. If we're given the long leg in number 5 of a 30, 60, 90 triangle, if you'd like to draw the picture, you definitely can. Otherwise, we have to remember, if we're given the long leg, we have to find the short leg first. To go from long leg to short leg, we have to divide by the square root of 3. We would then have to rationalize and then simplify. 18 over 3 can be simplified, so the short leg is 6 square root of 3. Now, the only one that we're missing is the hypotenuse. So we would double the short leg to find that the hypotenuse is 12 square root of 3. For number 6, we have an equilateral triangle, this moose warning sign. We know the height of the sign is 1 meter. Now, we have to remember equilateral triangles are also equiangular. So when we draw in our height, which is also called an altitude, we would be able to know that we would now be dealing with a 30, 60, 90 triangle. Because again, equilateral triangle is a type of isosceles triangle. So that vertex angle is bisected. So that's a 30-degree angle inside this triangle. We know it's 60 down in the bottom left corner. And we have the right angle because this is a height or an altitude. And what we're told to find is the length of each side, which it's calling S in this problem. So there is the variable we're trying to figure out. What we have to think about, though, is that within this 30, 60, 90 triangle, this altitude that we were given as 1 meter is our long leg, because it's opposite from the 60-degree angle. This side length, this S that we're told to find, is our hypotenuse because it's opposite the right angle. So we actually can't find what the side length is right away because we first have to figure out what that short leg is. So in this case, I just call this X. I have to first find that short leg before I can find the length of the hypotenuse. So going from long leg to short leg, I have to divide by the square root of 3, which then means I have to rationalize. So I have the short leg being square root of 3 over 3. Now the hypotenuse is always double the short leg. So 2 times the square root of 3 over 3. Again, remember that multiplying 2 times a fraction, 2 has a denominator of 1. So you can do numerator times numerator, denominator times denominator. We get 2 square root of 3 over 3. But now here's a case where you have to make sure you're reading the problem carefully. It says the side length needs to be found to the nearest thousandth of a meter. So you have to take 2 square root of 3 over 3 in your calculator, and you have to be careful with this when you type it in. You need to make sure you get 1.155 meters as your answer. So most people have scientific calculators. So how you would type this all in is you'd type in the 2. You'd have to hit a second button so that you get a square root. And now it opens up a parenthesis for you. You would put the 3 in. Now you need to close your parentheses after that. That's the one that most people forget. Then you hit your division symbol, and then you would be able to divide by the 3 in the denominator. You could also do 2 times the square root of 3, hit equals, and then divide that answer by 3 immediately without clearing your calculator, and you should also be able to get the correct value. Number 7, you're told that the distance from one corner to the opposite corner of a square playground is 96 feet. To the nearest thousandth, how long is each side of the playground? So the key to number 7 is if you're dealing with a square playground and you're talking about the distance from one corner to another, this is a diagonal, which ends up being the hypotenuse of the 45, 45, 90 right triangles that are created. So you're given the hypotenuse, you need to find a leg, which means you have to take the value of that hypotenuse, divide it by the square root of 2. So in this case, you're rationalizing by multiplying by the square root of 2 over the square root of 2, and then simplify. And then again, plugging into your calculator, you should have found that you'd have 67.882 feet for the length of each side of that playground. The last one that we're going to cover right now, number 8, says we have a garden shaped like a rhombus with a perimeter of 100 feet and a 60-degree angle. First thing I would always recommend in something like this is to draw a picture. So just quickly sketch yourself a rhombus. Show that one of the acute angles is 60 degrees. Now, in order to keep using all the information that I'm given, we're told the perimeter is 100 feet. So since a rhombus has all sides congruent, perimeter could be the same formula as it is for a square, so 4 times the side length. Plugging in 100, I'd be able to figure out that each side has a length of 25 feet. So I can label that in my picture as well. Now, the perpendicular height between the two bases, some people have difficulty understanding what that's talking about. So what that is basically a vertical line in this case, just because of how I have the rhombus drawn. It would end up being perpendicular to both the top and bottom sides of this rhombus, because those are parallel sides of a rhombus. So what it really creates is a 30, 60, 90 triangle that you know one of the side lengths for, and now you should be able to figure out that height between the two bases, what I have labeled as h. So please go ahead and do that right now. In order to find that height, we have to realize that the 25 feet we have here is the hypotenuse. We have the short leg, and then the height that we're really looking for is the long leg of that 30, 60, 90 triangle. So we first have to find the short leg by taking 25 and dividing it by 2. Hypotenuse is always double the short leg, so to go from the hypotenuse back to the short leg, got to cut it in half. And then we would take that short leg and multiply it by the square root of 3 to find the height in this case, or the longer leg. So a couple of ways that you could give your answer. So first of all, 25 over 2 is a terminating decimal, so I'm okay with you giving me the 12.5 answer. So if you take 12.5 and you multiply it by the square root of 3, your answer for the height would just be 12.5 square root of 3 feet. If you kept it in fraction form, 25 over 2 times the square root of 3. The square root of 3 has a denominator of 1, so that square root of 3 actually would become part of the numerator. So 25 square root of 3 over 2 feet would be the answer you could give there. And then also, because I don't specify whether you need to have your answer in simplest radical form or rounded to the nearest thousandth, you could type it in your calculator and tell me that the height is 21.651 feet. So like I mentioned before, this is where we are going to stop right now. If you need to go back and review anything that was covered, please make sure you do so.